Okay, Chapter 10, Section 2, Systems of Linear Equations in Several Variables. So this section is easy in concept. The ideas are very easy to explain. It's just a natural extension of what we did in 10.1. But the examples themselves can get pretty involved, and it's easy to sort of get lost in the mix of what's happening. So this is a fantastic section to teach people how to be very, very, very organized because they get ugly and it's easy to get lost in the middle of the whole thing. So we're going to be looking at solving linear systems. We're going to look at the number of solutions possible for a linear system, and then we can model using linear systems. So modeling refers to a word problem and application of the system. Okay, so first of all, distinction between linear equations and nonlinear equations. So remember that a linear equation in two variables was something of the form of y equals mx plus b. One linear. In two variables, we either saw it as y equals mx plus b, or if we solve for x, or not really solve for x, if we put the x and the y terms on just one side, another form of a linear equation we often saw was something of this form. Ay plus bx equals to c. Okay, so the characteristic that both of these versions of a linear equation have is that they both have two variables. We have constants, or the a, the b, and the c are just representative of constants. So for example, this could be like 3y plus 2x equals 7, for example, or negative 5y minus 8x equals 3/4, right? All of these are examples of this, which is a linear equation. But then as we move forward and we want three variables, well, the third letter that we would introduce is very often a z. So we could rewrite it this way. In three variables, we have a, y plus b, x, and then what do we do with the z? So I guess we need another constant in front of the z equals another thing. Okay, so there we go. So we can have it in three variables this way. So this is a linear equation involving three variables. So remember the y, the x, and the z are variables, whereas the capital A, the capital B, the capital C, well, I'm going to put lowercase d, equal constants. Right, so an example of something like this would be like 3y minus 2x plus 4z equals 9, for example. Something like that. We move over to this notation, where we stop throwing in an x, y, z, right? We just label them all x, but subscript them. X sub 1, x sub 2, x sub 3, dot, 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 all the way out to x sub n, right? So this is n variables into this equation. And then all the a's represent constants. A sub 1 is the constant in front of x sub 1. A sub 2 is the constant in front of the second variable, and so on and so forth. Good. This is in place of that. Of course, for 2 dimensions, we still love to use x and y. And for 3 dimensions, we still love to use x, y, and z. As you will see in this section, we use x, y, and z a lot. But once we move past 3 dimensions, we really abandon the x, y, and z notation and move over to this style of notation of saying the x sub 1 axes, the x sub 2 axes, the x sub 3 axes, and so on and so forth. Good. Linear equations. So here are some examples of what is a linear equation versus not a linear equation. So there's some key characteristics of linear equations. we can have 2, 3, 4, 5, right? The number of variables is not limited. However, with some basic algebraic manipulation, they must be able to fit this form. Note that in this form, the variables x1, x2, x3, they do not multiply. They all have power of 1. There's no roots in those variables, right? So those are all key characteristics of a linear equation. So here's some examples. You have x sub 1, x sub 2, x sub 3. Note that the x sub 3 is not inside the root. This is square root of 5 times x sub 3. I don't want to solve it the way they do. So let's just look at some examples. Okay, so here are some examples of systems of 3 equations with 3 variables. And these first few are pretty easy. They're in something we call triangular form because of this, right? They kind of fit this little shape of a triangle over here. It's like a little right triangle over here. And so these are really easy to solve because the last term has already been solved. The z is a 3 in question number 8. And so now if we do back substitution, we come back up here and replace the z with a 3, then we get a 12. That's going to solve for y, right? That's going to make it very easy to solve for y. And once we know y and we know z, we can go back up to the first equation, replace the z, replace the y, and then that'll make it very easy to solve for the x, right? So when a system of equations is already given to you in this format, back substitution makes it really easy to solve. Good. So I'm not going to do an example like that, so let's move on to one of these. Perform an operation on the given system that eliminates the indicated variable. Write down a new equivalent system. And let's just go ahead and solve it. They're just kind of doing baby steps for you to be able to solve one. So let's just jump to say like number 24. Find the complete solution to the systems or show that it is inconsistent. So let's see. X minus y plus 2z equals to 2, 3x plus y plus 5z equals to 8, and 2x minus y minus 2z equals to negative 7. Okay, so here's our system that we want to solve. And I don't know the answer, so I'm not sure if it even has a solution. It might be something that has no solutions. Remember, those are called inconsistent. Or it might be something that has an infinite number of solutions, which we call dependent. Or it might have a specific solution for these. Okay, so how do we solve it? We have 3 letters here, x, y, and z. If the original question is given to you in a slightly different format, then move them, do some algebraic manipulation to arrange them like this, such that we have the 3 equations with the equal signs right on top of each other, and then the letters in the same order. So x, y, z in all 3 of them. Okay, what you want to do is target 1 letter for elimination from 2 different sources, right? So by what I mean by that is that we have equation number 1 here. Actually, let's put it over here. Right. If I label these as equation number 1 is this one, equation number 2 is that one, and equation number 3 is that one. Okay, you're going to pick two different groupings. There are several groupings we could do. There are six groupings. Six groupings we could do. We could do equation number 1. Well, actually, no, three groupings. There's three groupings we can do. Equation 1 and equation 2. We could do equation 1 and equation 3. Or we could do equation 2 and equation number 3. Right, so these are the three groupings that we could do, either this one, or this one. It doesn't really matter which two you choose, but pick two of these, whichever two are the easiest, and target for elimination one of the letters, the same letter in both of them. So for example, let's say I just want to get rid of x. So I would pick, say, this one, this grouping, and just arbitrarily, why not, say this grouping. So eliminate x. So if we eliminate x, if we do that, we'll get a new equation that doesn't have any x's in it, right, from these two. And then the new equation will only have, so new equation, call it number 4, will only have y's and z's. And same thing over here, if I take these two equations and eliminate the x, I'll have a new equation, I'll call it number 5, that only has y's and z's. And then I'll be able to get these two and cancel out one of the letters, resulting in my solution from that point, right? So at this point it reduces down to a system of two equations, two unknowns, right? So now I'll have equation number 4 and equation number 5, and there'll be my new system with two equations and two variables. This is 10.1. We've reduced it from a 10.2 question to a 10.1. So then we do all the things we did before in order to do that. Good? So that's our plan of attack. Now, how can things go wrong? People make mistakes in the following way. They pair up a grouping, like let's say they choose equation 1 and equation 2 and they eliminate x. And then they choose equation 2 and equation 3 and they eliminate y. Okay, well now you have something that isn't useful, because now this one is going to eliminate y, which means you'll have a new equation that only has x's and z's in it, but now you have a new system that has x, y, z in it, all three variables. So that's not going to be helpful. Good. So you got to make sure that you eliminate the same letter both times. So that's one very common mistake. People start eliminating different letters. Okay. So that first grouping, you have to eliminate the same letter. The other mistake people make is that they grab the same grouping and they eliminate x, and then they grab the same grouping and they eliminate a letter, a different letter. I'm not sure. Something along those lines. And again, you're going to have a problem. Okay, so two different groupings. When we have three equations, there are three types of groupings you can do, and then eliminate the same letter. Good? Good? Okay, so let's do it. So let's do the first part of this. Let's call this single star. Right? Chapter 1, Section 1, single star. You got to subdivide your problem if it gets really, really big. Okay, so in this one, I want to take equation 1 and equation 2 and somehow cancel out the x. So let me bring those over here. Equation 1 is x minus y plus 2z equals to 2. And equation number 2 is 3x plus y plus 5z equals to 8. So here's my system of equations with equation 1 and equation 2. This one's equation number 1 and equation number 2. Okay, so in order for them to cancel, I need to multiply this equation by 3. Equation number, by negative 3. Number 1, I want to multiply it by negative 3. That'll result in a negative 3x in the leading term, and the negative 3 plus positive 3 will cancel out, so I know that that's how I can eliminate the x. So minus 3, let's do minus 3x plus 3y minus 6z equals to negative 6. Good. Equation 2 I'm just going to copy. I'm not going to do anything to it. Equation number 2. And then I'll get 3x plus y plus 5z equals to 8. Good. So go ahead and add these together, and these things cancel, and then this will be 4y, and then this guy is a minus z equals to positive 2. Okay, so that's my new equation number 4. Equation number 4. Okay, this one. And it only has z's and y's in it. Good. Now I want to come back over here and I want to do this work. I want to take equation number 2 and equation number 3, and I want to eliminate the x again. Right, so let's do that as a double star. Double star is going to be over here. Double star. And let me copy that over. I want equation 2 and equation 3. Okay, equation 2 and equation 3, that'll be 3x plus y plus 5z equals to 8, and 2x minus y minus 2z equals negative 7. So here's this system. Let's scoot over. And if I want to cancel out the x, I need them to have additive inverses as their coefficients. And looks like 6 is the least common multiple. So let's multiply this equation, which is equation number 2. I should label them, I guess. Equation number 2 is this one. Equation number 3 was that one. So I'm going to take equation number 2 and multiply it by negative 2. And then I want to take equation number 3 and multiply it by positive 3. So I'll end up with negative 6x minus 2y minus 10z minus 16 equals minus 16. Good. And then this one will be 6x minus 3y minus 6z equals negative 21. Good. So now I can add them. Minus 3 minus 6 minus 21 minus 16 minus 10 minus 2. Okay, so then the x's cancel, and I'll end up with negative 5y minus 16z equals to negative 37. Good. And that is my new equation number 5. Equation number 5 is this guy. Right, and it only has y's and z's in it. Let me zoom out a little bit more and get a sense of the bigger picture here. Okay. Alright, so we took equation 1 and equation 2, eliminated x. We got a new equation 4 that only has y's and z's in it, no x's. Then we took equation number 2 and equation number 3. We eliminated x. We got a new equation that only has y's and z's in it. Now we can set up a new system of equation, which has equation number 4 and equation number 5 in it, and then we can eliminate one of the variables to solve for the other one. Okay, so let me put that over here. Let's put it over here. So I will have the new system, which will be 4y minus z equals to 2, and minus 5 minus 16 minus 5y minus 16z equals to negative 37. Okay? Negative 37, yep. Okay. So this is my new system where this was equation 4 and this one's equation 5. Good. Okay, so now we gotta target this for elimination. We can cancel out the y's. Least common multiple is going to be 20. 4, 8, 12, 16, yep, 20. Or we can cancel these guys, and least common multiple is going to be just the 16. So I could multiply both of these by 16. Let's do that. Well, it's going to have to be the opposite sign. So let's multiply this equation, equation number 4. Let's multiply it by negative 16. That way we get positive 16 there, and then the z's will cancel out. And so I'll get negative 64y plus 16z equals negative 32. And then multiply this guy, get equation number 5. We're just going to copy it, not do anything to it. So we'll end up with negative 5y minus 16z equals to negative 37. So then when we add these guys, these will cancel. We'll end up with 69. Negative 69y equals to negative 69. And so y equals to negative 69 divided by negative 69. So y will equal to 1. Almost there. 1 out of 3. Good. So now that we have y equals to 1, we can use one of these other equations. How about equation 4? From equation number 4, we had 4y minus z equals to 2. But now we know that the y is actually a 1 times 4 minus z equals to 2. So 4 minus z equals to 2. So z equals to 2. Okay, so now we have 2 of them down. Now we can come back to any of our original equations. And we have 2 of the variables. We can solve for the x now. Let's go back to this guy. So let's say we take equation number 1 now. X minus y plus 2z equals to 2, right, from equation number 1. And now we know that the z is actually a 2, the y is actually a 1, minus 1 plus 2 times 2 equals to 2. So x minus 1 plus 4 equals to 2. So x equals to 2 minus 4 plus 1. X equals to minus 1. So we have our solution. Solution is the combination of these three, which we normally write in the order in the triple pair -1, comma 1, comma 2, where this is in the form of x, y, and z. Good. Any questions so far? If we can capture all of it in one screenshot, probably not. Almost. Yeah, yes. Okay, any questions? You can also check. Let's come over here and check it. Check. Is it true that x minus y plus 2z equals to 2? We have blank minus blank plus 2 times blank equals to 2. And is it true that if we insert a -1 and a 1 and a 2 times a 2, we get a 2? Right, so that'll be -1 minus 1, that'll be -2 plus 4 gets you to +2, so that works there. Then we have 3x plus y plus 5z equals to 8. So 3 times something plus 5 times something better be equal to 8. And let's make sure that this is in fact the answer. -1, 1, and 2. So that makes it -3 plus 1, that's -2. -2 plus 10 gives you 8. Yep, that works. And finally, 2 times x minus y minus 2 times z equals -7. So 2 times blank minus 2 times blank equals -7. And we have this, which is -1, 1, and 2. That would be -2 minus 1 makes it -3, minus 4 makes it -7. Yep, it worked out. Good. So we found the triple ordered pair that that solves this system of equations. Questions, 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 questions? So just like in chapter 10.1, sometimes there isn't a solution. Sometimes there isn't any point that solves all three equations at the same time. And when we're doing our algebra and we're working it all out, the way we will recognize that we have run into a situation where there is no solution is going to be that at some point, as we're working along our way and we're doing everything, all the variables will disappear, right? Like we'll come across and we're trying to cancel out the x, and maybe all three variables cancel out, and you'll just be left with a statement. And if that statement is false, it means there's no solution. So if I was trying to cancel out my x here, okay, let's multiply by 3, -3 multiplied by 2, and just kind of focusing on one of the variables. But then accidentally all the other ones lined up as well, and then all the other variables canceled, either at this stage or over here at this stage when I was just trying to eliminate my z's, right? I'm focusing on eliminating the z, but then when I go to take care of that, maybe the y's also cancel out, and instead you end up with a 0 equals something. Now, if it's 0 equals any other number other than 0, that means you have a false statement, and that means that you have no solutions. Good? On the other hand, if you're working your way through this process and again you accidentally cancel out all the letters, you know, unwillingly, it just happened, and you end up with 0 equals 0, now you have a true statement. That means that there's an infinite number of solutions. Good. Questions, 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 questions. Questions. No. Your book has some excellent graphs of what it would look like when that happens. Let's look at this. No, that's not it. Here we go. Some nice pictures of what it would look like. Okay. So, linear equations in 3 dimensions are called planes. They're like sheets of paper. So this is a linear equation. The pink one here is a linear equation in 3 dimensions, the blue one and the yellow one. So here's an example of 3 different equations in 3 variables. When we graph them, there is one single dot, right? One single point that will be a triple pair. One single point that solves all 3 equations. One point that is on all 3 planes. Good. We can have 3 different planes that intersect at sort of a line like this, and this is a case when there are an infinite many number of solutions, right? 3 planes intersect at more than one point. The system has an infinite number of solutions. Any point that's on that red line will be a point that's on all 3 planes, the blue plane, the yellow plane, the red plane. And so this is a case where those 3 equations are dependent on each other. They have an infinite number of solutions. Good. And here is a way of drawing 3 different planes such that there is no single point that crosses all 3 planes at the same time. Right? There's solutions to both the blue and the red one that would be on this line over here. There's solutions to the blue one and the yellow one. And there's solutions to the yellow one and the red one, but there isn't any solutions that would fit all of them. So we'd say that this system has no solutions. Good. Any questions on all that? So this is all very, very similar to 10.1, just the natural extension of that. I don't think the concept is more difficult. It's really the same ideas as 10.1. It's just that the equations, the systems get a little longer and it's easy to get lost in the whole thing. But if you're clean and neat with your work, very organized, you should be able to get through it. Okay, just don't make those common mistakes. Pick one letter. Now you can pick any letter you want. I just happened to pick X because it was just the first letter. But if you want to pick Y, Y looks very convenient to cancel. So pick whichever letter looks most convenient to solve, right? The numerical coefficients in front are convenient, nice, easy things to work with, and you can change it to any one of those letters. Okay, so pick one letter and eliminate it twice. Eliminate it with one pair, eliminate it with a different pair. That'll give you a new system of equations, and then again you have to start over and eliminate the missing value. I'm sorry, eliminate one of the variables to solve for it. Okay. Any questions at all? So we did 10.2 number 24, a system of equations like this. So let's look at a online graphing tool that will help us with 3-dimensional grids. I love Desmos for 2 dimensions, as we've used a lot, but they don't do well with 3 dimensions, not yet at least. So there's another program by GeoGebra. If you just put GeoGebra, type in GeoGebra 3D calculator, you'll get it. It's free. And then it helps you do a good job with graphing 3-dimensional things. So let's just type in x minus y plus 2z equals to 2. Okay, and this is what it would look like. Let me get rid of some of these things. This is what the graph would look like. This is a 3-dimensional image, right? So a linear equation in 3 dimensions is called a plane. And it just terminates here, but you can imagine this goes on forever at either end. Right? Every point on that blue sheet is takes 3 pairs, 3 numbers in order to arrive to a point on that blue sheet. Right? We have a value along the red, a value along the green, and we have a value along the blue. Good. Let's see if we can label the axes to see which one's which. Show axes. Oh, here's the axis. Show the axes. Grid. Show grid. Show plane projections in some settings. Axes is vertical. Label. Ooh. Show x-axis number positive distance. Label as the x-axis. Okay, so that'll label it. The y-axis, label it as the y-axis. And the z-axis, label it as the z-axis. There we go. So now we see that the blue one was the z, and the green one was the y, and the red one is the x. Okay, so here's one plane. Now we had 3 equations, so let's graph the other ones. And we have 3x plus y plus 5z equals 8. So there's another one. And the last one is equation number 3, which is 2x minus y minus 2z equals to -7. And they're all blue, so let's change that. How do we change that? Settings, color, one of the reds. You can stay blue, you can stay green, one of the greens. There we go. So here is the 3 different equations. Each provide you with a different plane. And as you can see, the only point where all 3 of them meet, the blue one, the red one, the green one, all of them meet at that little point right there in the center. Right? We know that that point from our solutions, that point was the point, what was it, -1, 1, 2. Whoa, what the hell just happened? Delete. The point -1, 1, 2. Enter. There we go. Okay, so there's that point. I don't know if the fact that the planes are really opaque is helping or hurting. You can also change the settings of that. Let's go over here and change settings, color. Let's make it dark, less opaque. Let's go here and let's make this one also darker. And over here, let's make this one also darker. Okay, so maybe that makes it a little easier. So you see that point A is on all 3 planes, right? I can eliminate the blue one, like stop graphing for a second, eliminate the red one, and you can see that that point is on the green sheet, right? It's a point on the green plane, so it's a point on equation number 2. Also, it's on the red one. You can eliminate all the other ones. You can see that that point, point A, is also on the red sheet, on the red plane, equation number 1, and also it's on the blue one. I can eliminate, well, that almost looks like black, right? It's a dark blue. Let's change the color on that skin, ugly. Color, how about that? Is that better? I wonder why it's so dark. Anyway, okay, it doesn't seem like the light blue, but At any rate, it's on this plane as well, and so it's on all three of them. If I turn them all back on, it's on the green one, it's on the blue one, it's on the red one. That point is the solution to the system of three equations. Good. Any questions about all this? No? No? You should go onto this website and play around with some of your equations. Oh, I guess it was like selected or something. That's why it was like a weird color. That's weird. Okay. Good. Good, good, good. Okay, let's play around with some of the other equations in your book. Type them in here and see what we get. I don't know, let's just pick one of these and see what happens. So we can very easily tell from graphing it if it's going to have a solution or not. It's infinite. Infinite solutions, no solutions, one solution. So let's take number 36, for example. 2x plus 4y minus z equals 3 is one equation. X plus 2y plus 4z equals 6 is another equation. And number 3 is x plus 2y minus 2z equals 0 is another equation. And let's get rid of this thing, since that was the answer to the previous one. Okay, so here is what that looks like. And just by looking at it, it looks like there will be an answer. There is a point in the center there that belongs to all three planes, correct? Maybe looks like it to me. Something right in there somewhere. It looks like there will be a solution to this. Okay, so that one's going to have a solution. So anyway, we can just play around with them real quick and see if you can find one that has no solution. See if we can just play around with these numbers and get to something that will have a solution. What happens if I just change the thing from this to like plus z? Changes the direction this way. Yeah, it's going to be hard to just play around with them on my own. Anyway, this is a good place for you guys to play. Go to this thing, and you can type in different equations and see what the grids look like, the graphs look like. Okay. All right. Meantime, we are just going to move on to the next and final section we're going to do in Chapter 10. Let's get rid of that. Let's get rid of that. Let's leave. And we're going to go to section 10.7. All right. Okay, chapter 10, section 7 is on partial fraction decomposition. We're going to look at distinct linear factors, repeated linear factors, irreducible quadratic factors, and then repeated irreducible quadratic factors. Okay, so we'll look at what those mean and how we use them. That's what this section is about. Pretty easy. The implementation is not so easy, but okay. So what happens is that so far we have in algebra spent quite a bit of time learning how to add fractions, right? So let's do an extra simple example on the side. You know, how do we add 1/2 plus 1/5, right? So of course we needed to learn that. We need a common denominator, right? So, okay, so we needed to learn this whole process of getting a common denominator, multiply this by 5 over 5, multiply this by 2 over 2. We get to two equivalent fractions. This one becomes 5 over 10. 5 over 10 is another way of saying 1/2, so that's an equivalent fraction. 2 over 10. 2 over 10 becomes another way of describing 1/5, another equivalent fraction. And now that they have the same denominator, we're able to combine them, and this turns into 5 plus 2 over 10. Good? All right, well, the same concept applies when it gets a little more complicated. If we have 1 over x minus 1 plus 1 over 2x plus 1, then again we need a common denominator. By default, if we can't figure it out, one easy way to do it would be just to multiply these two together. So we multiply this one by 2x plus 1 over 2x plus 1. Multiply this one by x minus 1 over x minus 1. And now we'll have a common denominator, which will be the product of these two under both fractions. So this fraction will become 2x plus 1 divided by 2x plus 1 times x minus 1 plus, and this one will become x minus 1 divided by 2x plus 1 all over x times 2x times x minus 1. Okay, so they have the same denominator, so now we're able to add them together and get 2x plus 1 plus x minus 1 all over the combined product of the two of x plus 1 times x minus 1. Good. So now we just simplify the numerator, combine like terms, distribute if you need to, and we end up with 3x over the product of the two, which is 2x plus 1 times x minus 1. Good. And that's where this is coming from. Easy, easy, easy breezy. Okay, so what are we going to do? We are, in this section, interested in going backwards. Just about any time you learn a process in math in one direction, inevitably, at some point, someone will ask you to undo it and go backwards, and that's what we're going to do here. So we've learned how to go from this statement down to this statement. So now we want to go backwards and start here and end up over there. We want to separate the fraction into the summation of simpler fractions, right? Partial fraction decomposition. So we want to start here, and work our way backwards to get to this. That's the goal of this section. Okay, start with ugly, ugly fractions and break them up into a summation of simpler fractions. As many simple fractions as are needed. So maybe the summation of 3 fractions, or 4 fractions, or 5 fractions, anything, such that the summation of all those fractions ends up equaling the more complicated fraction you started with. Okay? Good, 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 good. Okay, that process is actually pretty hard to do, as you might imagine. So what we do is we break it up into certain types, certain pieces. right? And we're going to rely on some formulas to be able to do that. So let's see, let R be a rational function such that R of x equals to px over q of x, where the degree of p of x is less than the degree of q of x. Okay, so if we have a rational function like this, so it's a polynomial over a polynomial, and the degree of the polynomial is less than the degree of the polynomial in the denominator. By the linear and quadratic factors theorem, every polynomial with real coefficients can be factored completely into factors of the form ax plus b, so linear factors, or this form, which is quadratic factors. So for instance, if we start off with x to the 4th power minus 1, we can factor it all the way down and break it all the way down into something like this, not allowing ourselves to go any further because then we'd have to go into imaginaries. We want to avoid that here. Okay, so the methods of partial fraction decomposition indicate that after we've completely factored something, we can express it like this. So a over ax plus b to the power of I, and ax plus b over lowercase ax squared plus bx plus c to a power of j. Right? I know this looks a little confusing right now. We're going to break this down even further in a second. But the capital letters here, the A here and the B, represent constants. So it's indicating for us that when we break it up into a summation of smaller fractions, those smaller fractions will be either of this form or of that form. Good? Good? Maybe kind of? I think that's still a little confusing. Let's just dive into the first type. So here, this is what the first type is going to be. If we can break up the denominator into distinct linear factors like this. So linear factors, we can completely factor it out and we end up with distinct linear factors like this. Then we can rewrite our original ugly fraction into a summation of a bunch of easier fractions where the denominator for each one of these is one of those distinct linear factors of the denominator, and there is a bunch of constants in the numerator. Capital A sub 1 through capital A sub n are just constants that we need to solve for. Okay, I think maybe I might still be losing people. So let's just dive into an example, right? Nothing like just learning by example. So we have one big, ugly, nasty fraction, and we want to be able to break this down into the summation of a bunch of simpler fractions, right? Not only for fun, yes, fun is a really good reason to want to do this, but also you'll find that there are some areas of math where that becomes very beneficial to do that, and in particular calculus. There's some stuff in calculus where you'll run into it and they'll say, okay, use partial fraction decomposition to break this up into simpler fractions, and then that's useful in calculus. Okay, so the first thing we need to do, step 1, is factor the denominator. Okay, so factor x cubed plus 2x squared minus x minus 2. Okay. There are 4 terms, so I think factor by grouping is a pretty good option. Let's see if that works out. So factor by grouping, I'm going to focus on the first 2 terms, see what they have in common. They have an x squared in common. So I'll factor that out, just the first 2 terms, leaving me an x plus a 2 plus blank copy x plus 2, right? A plus a blank space I'll fill in a second, and then I copy this binomial. It's got to be copied because the next step after this is going to be to factor it, so these two have to be identical. Now the next step is to fill in the blank by looking at these 2 terms, the last 2 terms of the original polynomial, and I have to ask myself, what can I put in here to make this a true statement? So that blank times x equals this term, and blank times positive 2 equals that term. So this one's pretty easy. It looks like just a negative 1. Good. Now I factor out the x plus 2. X plus 2 gets factored out, and what remains is an x squared minus 1, which I know is a difference of squares. So I know that that can be factored as x plus 1 times x minus 1. Good. Difference of squares. Good. So I've completely factored out the denominator. Any questions about that? No? No. Okay, so let's see what we have so far. We have that the original, which was 5x plus 7 over x cubed plus 2x squared minus x minus 2. So far we have that that original fraction is equal to this one, x plus 2, x plus 1, x minus 1, and there's a 5x plus 7. Okay, so this equals that. All right, now, according to the blue box right above us, when we're able to break up the denominator into distinct linear factors, right? Each one of these is a linear equation, right? It's a linear factor, and they're all different. So distinct linear factors. Okay, that means that this can be broken down into 3 separate fractions, where the denominator of each one of these fractions is equal to one of the linear factors, like this. Okay, I put each one of these in the denominator of each of my fractions, and there will be an unknown value here, a, b, and c, which are constants. And they're to be solved, constants to be solved. Good, like maybe this is like a 3 and a 2 and a -1, for example. I don't know, right? There's constants to be solved. So far we're okay? Questions? No questions? I'm just copying it again. X plus 2 plus b, x plus 1 plus c, x minus 1. And so now what I'm going to do is I'm going to multiply both sides of the equal sign, let's make it in blue, by the denominator, right? I want to solve for a, b, c, such that this is true. So I'm going to begin by multiplying this side by x plus 2, x plus 1, x minus 1. If I multiply by these 3 terms, then all the terms of the denominator on the left-hand side cancel, right? And I'm going to do the same thing on the right-hand side, multiply all of it by x minus 2, x plus 2, x plus 1, x minus 1. Good. So on the left-hand side, everything cancels, leaving me with just the 5x plus 7. I don't know why I wrote it way over there. Leaving me with the 5x plus 7 equals, and now I got to distribute all of these. All of these gets multiplied into each of these fractions. So I'll end up with a over x plus 2 times x plus 2 times x plus 1 times x minus 1 plus b over x plus 1 times, and then all 3, x plus 2, x plus 1, x minus 1 plus c over x minus 1 times x plus 2, x plus 1, x minus 1. Good. Now a bunch of stuff will cancel. X plus 2 cancels there, x plus 1 cancels there, and x minus 1 cancels there. So I end up with, on the left-hand side, I have 5x plus a 7 equals to a times, and that'll be x plus 1 times x minus 1 plus b times x plus 2 times x minus 1 plus c, and it's x plus 2 times x plus 1. Good. 5x plus 7 equals 2. And then, well, this is a difference of squares, so I know it's really going to be a times x squared minus 1 plus b times, and then if I FOIL this guy out, I'll get an x squared minus x plus 2 gives you plus x minus 2. Plus, and then a c, and then if I FOIL this out, I'll get an x squared plus x plus 2 gives you plus 3x plus 2. Good, 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 good. Okay, this is the tricky part. I'm going to continue to distribute this. So I'll end up with capital A x squared minus capital A plus capital B x squared plus capital BX minus 2b plus cx squared plus 3cx plus 2c. Okay? Alright, so what I'm going to do is I'm going to group up the terms based on the powers of x. So I'm going to just bring together all the ones that have an x squared, all the ones that have an x, all the ones that have just the letters, just the constants with no x to the 0 power. Okay, so I'm going to write these, and these together, kind of group them up. And I'll end up with ax squared plus bx squared plus cx squared. Good. And then I'm going to group up all the terms that don't have, that just have a power of x on it on their own. So I have x to the power of 1 there, and I have this one, right, x to the power of 1 there. So those will turn out to give me bx plus 3cx. Okay, that's those. And then all the other ones that survive that don't have a power of x. Minus a doesn't have a power of x. Minus 2b doesn't have a power of x. And plus 2c does not have a power of x. So minus a minus 2b plus 2c. And on the left-hand side, I'm going to leave this alone, like that. So I'm going to do one more step. Now I'm going to factor out the x squared from these 3 terms. From those 3 terms, they all have an x squared, so I can rewrite it as a plus b plus c x squared plus, and now these 2 terms both have a power of x. I'm going to factor those out. I'll end up with a b plus a 3c x, and then the rest of it. And I'm going to group them up in the following way. Plus, and then I'll put a minus a minus 2b plus c, plus 2c, like that. Good. And now the really, really interesting yet tricky part is to note the following. On the left-hand side, I'm just leaving it alone, and I'm going to group these up in the following way. This is a very powerful statement, right? They're equal to each other. Everything on the left-hand side equals the right-hand side. So it must be true that, let's looking at this one, the constant in front of the x to the power of 1, that must be this. The constants in front of the x to the power of 1, they must be 5. So I'm going to group those together and say that 5 is equal to b plus 3c. Good. and the constant with no variable, no x's at all, is a 7. It must be true that all of this over there, it better be a 7. I got to find the values of a, b, and c such that these things here give me a 7. These things here, these constants, give me a 5. So I'll get that 7 is equal to negative a minus 2b plus 2c. Good. And then the really tricky one is this one. What do we do about this? Well, notice that the x squared term is absent on the left-hand side. It's not there. So that means I can introduce it as a 0. 0 times x squared plus those terms. And now I get to combine it with that 0. Right? It must mean that these guys add up to 0. So it must mean that my third equation is 0 must be equal to a plus b plus c. Right? That's the really tricky part of this section right here. The regrouping of these terms this way, that gives you a new system of equations. Any questions, any questions, any questions, any questions? No? No? Okay, so now we have a new system to solve, and once we solve this system, we'll find the values of a, b, and c, and we can go back to our original statement and be able to complete the exercise. All right, so here's our system of equations, and I'm just going to mess with it a little bit, just rearrange them, just scoot them a little. Notice that there is no term a here, so I can just kind of create some space. And to put it in the same way that we've been solving things so far, let's write it as a plus b plus c equals 0, and then b plus 3c equals 5, and then minus a minus 2b plus 2c equals 7. Right, so here's the system we want to solve. So that would be equation number 1, equation number 2, and equation number 3. Okay, so noticing that if I grab equation 1 and equation 3 and cancel out the a, which is pretty easy, I would end up with a new equation that only has b's and c's in it. And equation number 2 already only has a b and a c in it. So then that would give me a new system that only has 2 variables. Good, so that's what I'm going to do. I'm going to take equation number 1 and equation number 3, equation number 1 and equation number 3, and I'm just going to add them. They already have additive inverses anyway. A plus b plus c equals 0, and minus a minus 2b plus 2c equals 7. So if I add these two, the a's cancel, giving me minus b plus 3c equals 7. Good. I'll call that equation 4 now. Equation number 4. And there's no need for me to go back and deal with another grouping of these two pairs to cancel out the a, since this one has already eliminated the a for us. Good. So now I'm going to take equation 2, which is b. Oops. So now I'm going to take equation number 2, which is b plus 3c equals to 5. And then I'm going to take equation number 4, we just discovered. Equation number 4, which is this minus b plus 3c equals 7. And, well, not much work needs to be done. It's a pretty easy question. So then the b's cancel. We end up with 6c equals 12. Therefore, C equals to 12 divided by 6, or C equals to 2. Right, so we got our first break, we got that one. And once we have C equals to 2, I can go back to equation number 2. Using equation number 2, we have B plus 3C. B plus 3C equals to 5, but we just discovered that the C is actually a 2. So we get that B plus 6 equals 5, so B must be equal to -1. So now we have 2 of them. And then we can go back to, say, equation number 1. A plus B plus C equals 0. Equation number 1. And now we can solve for A, since we know that the B is actually a -1 and the C is actually a 2. We get that A plus 1 must be 0, therefore A must be -1. Good. So we get -1, -1, and +2. Good. Questions, 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 questions? Okay, we can check our system to make sure that it works out there. Let's zoom out here a little bit. So we can check against our system. Check. Let's see, blank plus blank plus blank equals 0. And also blank plus 3 times blank must be 5. But also minus blank minus 2 times blank plus 2 times blank must be 7. And let's see if these all make sense. -1, -1, and 2. -1 and 2. -1, -1, and 2. Okay, so -1 plus -1 gives you -2, plus 2 gives you 0. That works out. That makes it 6, and -1 gives you 5. Yep, that works out. This gives you +1, and +2 gives you 3, and then 4 makes it 7. Yep. Okay, so I feel pretty confident that I was able to solve the values of A, B, and C that solve this system, but that was really just a means to a method here. There's a larger problem we're trying to solve. Going back to the original question, we were given this ugly, nasty fraction. We were able to factor the denominator completely so that the original fraction was turned into this one, where all we did was replace the denominator where this polynomial, third-degree polynomial, was replaced as the product of these 3 linear factors. Right? And so we were able to separate this into the summation of 3 separate fractions where each one of these factors is the denominator in one of those fractions. And after all this work, we just realized that this guy right here is actually a -1, this guy is a -1, and this guy is a 2. Right? A was equal to -1, B was equal to -1, and C was equal to 2. Good. So to put the whole thing back into the original statement, it is that 5x plus 7 divided by x cubed plus 2x squared minus x minus 2 is actually equal to the summation of these fractions, x plus 2 there, the -1, and then plus -1 there, with an x plus 1 here, plus a 2 divided by x minus 1. Right? So we were able to separate this pretty ugly fraction into the summation of 3 more simple looking fractions. And again, you could do a check on your work by figuring out what this is. How do you combine these? Again, the least common multiple would be to multiply all three of them and get a common denominator, bring them together, and after all that work, you'll see that it equals this. Okay, so that's a pretty ugly question. Pretty intense, lots of pieces. You got to be able to factor. So we're going to use all our factoring techniques to be able to factor the denominator, factor the numerator. Good. Note that this process is valid for cases where the numerator has a degree that's smaller than the denominator. Good, 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 good. If that's not the case, then that means that you can actually divide and simplify your result. So we might look into an example like that. Divide first, use synthetic division, long division, or long division of polynomials, and divide it into something simpler and then apply this process. Any questions at all? No questions, no questions, no questions. No? Okay, let's see what your author did. Similar, I'm sure, but maybe a little neater. Whoa. Okay, so your author did the exact same thing, factored the denominator, and then this chapter is telling us exactly this, that if we are able to factor the denominator into a multiplication of linear factors like this that are distinct, none of them are identical, then we can rewrite our original fraction as the summation of different fractions, 3 in this case, where the denominator of each one of those fractions is equal to one of the factors of that denominator. Good. So from that point on, once you've set it up, then you just have to find the values of A, B, and C that make this a true statement. Multiply both sides of the equal sign by the product of these 3 factors, and you end up with something pretty ugly, right? So this is what I wrote, just a little nicer. Factor, and then the next really brilliant piece is that after you multiply, combine like terms and everything, you want to come back and regroup them by powers of x. X squared, x to the power of 1, no x. Bring them all together, and then you'll end up with a system of equations that you can solve. And you end up with the same answers I did. They're in slightly different order, but that doesn't matter. The one with the x minus 1 has the 2, and the other ones have a minus 1. Good. Any questions, 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 questions? Okay, so the next case will be, well, what if they have repeated linear factors? What if after you factor it all out, one of those linear factors has a higher power? Okay, so case 2, the denominator is a product of linear factors, some of which are repeated. So if we have repeated linear factors, then this is what we have to do. We have to add more fractions to the mix. We add all of the fractions leading up to the power that's represented in the factorization of the denominator. Good. So here's an example. So this is the original fraction, right? It's a big, ugly fraction. We want to try and simplify it. And notice that x minus 1 is repeated 3 times. It's to the power of 3. Good. In the previous example, there were each of the factors was unique. We had three factors, x plus 1, x minus 1, x plus 1. Here we only have x and x minus 1 as factors, but x minus 1 is repeated 3 times. So what this property is telling us is that we have to provide a fraction for each one of the factors, x minus 1, for each one of the powers starting at 1, leading up to 3, which is the power represented in the factorization form. Okay? So this is saying that when I try and solve this, this is how I'm going to set it up. X squared plus 1 all over x times x minus 1 to the power of 3. is equal to, now I'm going to have one fraction for just the x, plus, and then I'm going to have one fraction for the x minus 1 to the power of 1, plus I'm going to have one fraction for the x minus 1 to the power of 2, plus I'm going to have another fraction for x minus 1 to the power of 3. Good? So because there's a 3 here, we have to have 3 different fractions. The power of 1, the power of 2, to the power of 3. If this had been a 4, you guessed it, then we'd have another one over here that has 1 over x minus 1 to the power of 4. And each one of these is going to have some constant, a, b, c, d, that needs to be solved. Good. Just like before, we need to multiply both sides of the equal sign by the appropriate thing to cancel the whole thing out. So here, let me copy the whole thing again. We have x squared plus 1 over x times x minus 1 power of 3 equals, okay, so on this side I'm going to multiply it by x times x minus 1 to the power of 3, and that'll cancel everything here. Now, when I multiply the right-hand side, I'm going to distribute. So I'm just going to make some space. B over x minus 1. C over x minus 1 squared. And D over x minus 1 cubed. Okay, so when I multiply the right-hand side, I distribute, and then each one of these terms will be multiplied. Okay, well here, all of that cancels completely. Here, almost all of it cancels, except that one of them remains, right? It's a power of 1, so it'll still be an x minus 1. Here, only one of them canceled, so an x minus 1 squared survives. And here, that cancels, so an x minus 1 to the power of 3 survives. Good. Okay, so we're left with x squared plus 1 is equal to a times x minus 1 to the power of 3, okay, plus, and then bx times x minus 1 squared, plus cx times x minus 1, plus dx. Good. So we're going to have to FOIL that guy, figure out what that is, and work our way through it. So x minus 1 to the power of 3, let's just break it down into pieces. X plus 1 equals to a x minus 1, and then it's x minus 1 times x minus 1. X minus 1 times x minus 1, right? That's all 3 of them. If I just get 2 of them, that'll be x squared minus 2x plus 1. And then all of that gets multiplied by x minus 1. So then if I distribute, I'll end up with an x cubed minus 2x squared plus x. And then the minus x squared plus 2x minus 1. So all of that turns into x cubed minus 3x squared plus 3x squared, oh no, 3x minus 1. So all of that is just FOILing out this x minus 1 to the power of 3. So I'm going to just repeat that down here. I'll end up with x squared plus 1 is equal to a times all of this, x cubed minus 3x squared plus 3x minus 1. Good. Any questions? Okay. Plus, and then we end up with a bx times x squared minus 2x plus 1 plus a cx, x minus 1, plus a dx. Okay, so now if I distribute, I'll end up with ax cubed minus 3ax squared plus 3ax minus a plus bx cubed minus 2bx squared plus bx, right, distributing this, I get these, this one, and this one. And then the cx gets distributed, and we end up with cx squared minus cx plus dx. Good. On the left-hand side, again, we have x squared 1. And I see powers of 3, so I already know that that means I'm going to insert a 0 times x cubed plus x squared. But there's also powers of 1, and there is no 1 over there, so I know I'm also going to insert a 0. So 0 times x cubed plus x squared. And then I'm going to insert another 0 plus 0 times x plus 1 equals. And then on the right-hand side, I'm going to again group them by powers. So all the ones that have an x cubed, that one has an x cubed, that one has an x cubed, and that's it. So I'll end up with a plus b x cubed. Good. Then all the ones that have x squares, like that one, and that one, and that one, that should be 1, 2, 3 of them. And I'll put a plus parentheses minus 3a minus 2b plus c x squared. Good. Okay. And then I'll look all the ones that have a power of x. So that one has a power of x. 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 So it'll be plus, and I'll end up with parentheses 3a plus b minus c plus d times x. Good. And then finally the constants. So there is a minus a, so plus minus a, and that's it. Yep. It's the only one that survives as a constant with no other power of x. Good. So hopefully I did that right. And then we get to do groupings. Good. So this 0 is the term in front of the x cubed, and here's the x cubed, so that must mean that 0 equals to a plus b. Good. And 1, there's an invisible 1 there, 1 is the term in front of the x squared, so that means that this whole thing must be equal to 1. 1 equals to minus 3a minus 2b plus c. 0 is the term in front of the x, so all of that must be equal to 0. 0 equals 3a plus b minus c plus d. And finally, let's go to that guy. There's only one variable that doesn't have a power of x, it's that one. So we should get that the minus a equals 1. I don't know why I flipped it around. Minus positive 1 equals to minus a. Positive 1 must be equal to the minus a. Wait, what? It is, whatever. It's to the minus a. So this would be a fairly simple one to solve since there's only two ugly equations. There's a has been solved. We can get B from there pretty easily. And once we find the A and the B, we should be able to find C from here. And once we find A, B, and C, we can find D from there. Good. So this is one of those triangular forms I mentioned before. We can convert this over here. I'm just going to rewrite it as 3A plus B minus C plus D equals 0, the one with all four variables. And then the one with three variables, we had minus 3A minus 2B plus C equals 1. The one with two variables, we have that A plus B equals 0. And then finally, the one with one variable, we have that minus A equals 1. Right, so here's just another way of describing it, rewriting this, and see how we can form a triangle, right? It's a system of equations in triangular form, which means that back substitution will work, right? It's a fairly easy way of solving it. So obviously, negative A equals to 1 means that A is equal to negative 1. So we have one answer. And then A plus B equals to 0 means that negative 1 plus B equals 0. Therefore, B must be equal to positive 1. We have two of them. And then minus 3A minus 2B plus C equals 1. So minus 3 times negative 1 minus 2 times positive 1 plus C must be equal to positive 1. So this is positive 3 minus 2 plus C equals 1. So that must mean that C equals to 0. So we have two of these. And finally, we can go to our last one. Hope I didn't make a mistake. These things are so long, you make one tiny little mistake and then the whole thing unravels. So hopefully we haven't made a mistake yet, or me. And then finally, looking at that first equation, 3A plus B minus C plus D equals 0. And we have that A was negative 1, plus B was positive 1, minus C was 0, plus D equals 0. So that must mean that negative 3 plus 1 plus D equals to 0. That's going to be negative 2 plus D equals 0. So D must be equal to positive 2. Okay, so those are the answers I'm getting. Negative 1, 1, 0, 2. So going back to the original question, negative 1, 1, 0, 2. That means that these guys are those values. Negative 1, 1, 0, and 2. Right, so since it's 0, it means it's a fraction. 0 over anything is still 0. So that means that this whole thing doesn't exist. And so I'm ready to answer the final question here, the whole thing. It's x squared plus 1 over x times x minus 1 cubed is equal to negative 1 divided by x plus 1 divided by x minus 1 plus 2 divided by x minus 1 cubed. Questions, 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 questions? No? 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 Okay, so let's see if that part's correct. Let's just check and see what the author did. Oh, a lot of space down here. All right, so your author broke it down again, same way, A, B, C, D. Notice that there's a separate fraction for each of the powers represented, starting at 1 and going up to 3. Multiply both sides by the denominator. You end up with this crazy ugly thing. We end up with the same terms. Break it down by pieces. We end up with this. It's a triangular one. A equals -1. B equals 1. C equals 0. D equals to 2. And so that means that the term with the C equals to 0 disappears, and we're able to rewrite our fractions this way. Right? Same answer. Any questions? No? No. Okay. The next type of thing we got to run into is irreducible quadratic factors. So you start factoring away your denominator, and you might end up with a quadratic that doesn't factor nicely any further. You can continue to try and factor it, but you might run into imaginary numbers, and we want to avoid those. We want to stay in the real number set for now. So when you run into a quadratic that is irreducible, you can't factor it any further without going into the imaginaries, then you leave it alone, and that's how we're going to deal with it. However, this means that one of the fractions that you have to put has to have a linear factor in the numerator. Okay. For example, let's say we're dealing with this guy here, okay, and we wanted to factor it some more. Okay, step 1 is to recognize that the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator, so that's good. Now we got to factor the denominator, so that's easy. That's just going to be factoring out an x, right? So let me rewrite it over here. 2x squared minus x plus 4 all over x cubed plus 4x equals, okay, that'll be 2x squared minus x plus 4. And I'll factor out an x, and that'll give me an x squared plus 4. Right? And we know that that does not factor any further. If it was an x squared minus 4, then it would factor. But x squared plus 4 does not factor any further. Okay, so what this theorem is saying is that this is going to break down into two separate fractions where we have a term for the x, and we'll have a separate fraction for the x squared plus 4. Right? So one for the x squared plus 4. The difference is that because this is not linear, then up here, this will not be linear either. I'm sorry, because this is not linear, that means this will be linear. This is linear means that there is just a constant here we need to solve. And I'm just going to pick the letter C, I guess. Right? Some constant over x, just like we've been doing. But this time, this is not a constant. This is a linear equation that belongs there because this is an irreducible quadratic. Right? That's what this is telling you right here. That this will reduce this way. Any questions? No? So just keeping the part I want to work with, we have this minus this plus this all over this equals to c over x, ax plus b, all over x squared plus 4. Okay, so now I'm going to multiply both sides of the equal sign by the x times an x squared plus 4. Multiply all of this by x times x squared plus 4. And then on the left-hand side, everything cancels, just like before. So we end up with a 2x squared minus x plus 4. And then after I distribute this, I'll end up with a c times x squared plus 4, right? Because the x's will cancel when I distribute. Plus, and I'll end up with an ax plus b times an x. right? Because the x squared plus 4s will cancel. Good. Okay, then everything else is exactly the same as before. We need to distribute combine like terms based on powers of x and solve the resulting system of equations. Okay, distributing the x, distributing the c, I get these guys. Now I want to combine them by powers of x, so 2x squared minus x plus 4 equals to a plus c times x squared. That takes care of these guys. X squared and the x squared. And then there's a bx plus 4c. Okay, so then that's when I group them up. It must be true that the 2 is equal to the a plus c. 2 equals a plus c, right? Because they're both the numbers in front of the x squared term. It must be true that the b is equal to -1, since it's the only one that has a term of x to the power of 1. Good, so that's easy. -1 must be equal to b. And finally, the 4c must be equal to 4. 4 equals 4c. So this is an incredibly easy system to solve. So c must be equal to 1. b equals to -1, we already have that. And from here we have that 2, well, let me get it right. We have that 2 equals to a plus c, but the c was a 1. So a plus 1 equals to 2, so a must be equal to 1. So 1, -1, 1. Now we have to be careful about how I resubstitute them in here because of my choice of what the a, the b, and the c are. Right? So being careful, I know that the c was a positive 1 there, the a was a positive 1 there, and that the b was a -1. Okay, so 1, 1, -1. So let's write the original thing. That means that my conclusion is that the original question, the original fraction given, the original rational fraction, rational function, so this guy is equal to 1 over x plus 1x, that's just x, minus 1, all over x squared plus 4. And that's our answer. Any questions? No? No. Let's make sure the author did the same thing. Factored it. See, we end up with a linear numerator with an a and a right. So the author switched around the a, b, and c, but it doesn't matter. You just have to be consistent about it, and when you come back and plug it back in, you'll get the same answer. Okay, so we get that. Distribute, combine like terms. A plus b must be a 2. A c must be a -1. And before a must be equal to 4, so his a was equal to 1. Okay, so we get the exact same answer. Questions, 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 questions? No? No? Okay, the last thing is to consider a combination of these things where we have repeated irreducible quadratic factors. So we end up with quadratic factors, and some of them have a power, right? They don't factor any further. So if we have an irreducible quadratic factor, a quadratic to the power of k, just like before when we had a repeated linear factor, we need to include a fraction for every single one of those denominators raised to the power of 1, 2, 3, all the way out to the power of k. Good. So like this. Except that now we don't just have constants in the numerator, we have a linear equation for each one of the numerators. So as you can imagine, these things get really nasty. So once we get to this level, you really wouldn't be asked to actually solve it. You would just be asked to write down maybe some part of it, like maybe just write out what it would look like, the form, or maybe just get it down to a system of equations and then stop. Maybe at that point you can transition over to technology or something to help you solve the system of equations that results from that, but it could be pretty ugly, right? It's a really big, it could be a really big system. So here's an example. So notice that it's already been, this fraction is already given with the denominator factored out. So here I saw that the answer is already there, so I don't want to ruin it. So there's going to be a different fraction for each one of these powers because it's repeated up to a power of 3. So it's going to be a fraction with an x plus a fraction with an x squared plus a fraction with an x cubed. Right? That's how we deal with these powers. Next, there's going to be a fraction with this, right? This is a quadratic that cannot be reduced any further. So there's going to be a fraction that has an x squared plus an x plus a 1. Good. And now here's another quadratic that cannot be reduced any further. It's to the power of 3. So again, we're going to have one fraction that has an x squared plus 2. We have another fraction that has an x squared plus 2 to the power of 2. And finally, we're going to have 1/3 fraction, final fraction, that has an x squared plus 2 to the power of 3. Good. Now, all the ones that have a linear in the denominator are just going to have constants up here, like a, b, c, like that. Right? So one single number goes there. And then all the ones that have quadratics are going to have a linear equation that comes up here. So we'll have maybe like a dx plus e plus e. And then here we need x plus x plus x plus c, d, e, f, g, h, I, j, k. Well, that's ugly. We got to find a lot of letters. The A, the B, the C, the D, the E, the F, the G, the H, the I, the J, and the K. That is a really, really, really ugly system of equations that we're eventually going to have to solve. Good. So that's what this is saying. Of course, we would not ask you, I would not ask you to solve this by hand. That is ugly. But if we had access to a program that did it, we can set up the system and then just type it all in there and have the system solve it for us. Good. Any questions? No? The pattern seems good. Factor the denominator, I mean, that on its own can be a lot of work, right, to find the factorization. Okay, so I am done with this section. I don't know if you feel like doing one more example or if you feel like ending it a little early. How do you feel about this section, guys? Feeling okay with it? Just want to try it on your own? Or do you want me to do one more? Anybody?